Base your answers to questions 16 and 18 on the information in this diagram. A ball is thrown horizontally with an initial velocity of 20 meters per second from the top of a tower 60 meters high. You may use g equals 10 meters per second squared and neglect air resistance. The question says, what is the approximate total time required for the ball to reach the ground? In order to do this calculation, we're going to use the equation dy is equal to 1/2 g, or a, t squared. When we rearrange the equation, we get t is equal to the square root of 2 dy over g. So that's equal to the square root of 2 times 60 divided by 10, which is equal to the square root of 12. So the answer to that is about 3.5 seconds. Using the same information, the next question says, what is the vertical velocity of the ball just before it strikes the ground? Well, we can use V final is equal to V initial plus GT, or AT. Either one, AT or A and G are the same. This is 0, so we can neglect it, and we end up with V is equal to AT, so it's equal to 10 meters per second squared times the 3.5 seconds that we came up with in the previous question, so we end up with 35 meters per second squared. There's another way that we can do this equation as well. We can do this equation with velocity is equal to the square root of 2 times g times dy, and that's equal to the square root of 2 times 10 meters per second squared times 60 meters, and we end up with about the same answer, meters per second, 35 meters per second squared. The number is actually exactly the same, but there may be a little bit of rounding error. The second question says, what is the horizontal velocity of the ball before it reaches the ground? And this is important right here, the horizontal velocity. Okay, so pay attention to that word. Horizontal velocity, that's this velocity right here, 20 meters per second. Well, horizontal velocity is unaffected by gravity. So the horizontal velocity is constant, and it remains 20 meters per second all the time. There are no changes. So this velocity stays the same. There's no calculation involved. In this diagram, it says, what do each of these represent? A, B, C, and D. So, A, B, C, D, and E, I should say. So, A is the normal force. D is equal to force X. It's in the X direction if you look at this right here as being your axis. Okay? If this is X and Y, then this is force in the X direction. C over here is the force in the Y direction, so we could call that force Y if we wanted to. This E right here, this right here is the force of gravity, and B is the force of friction. The most important ones to note are this one here, which is gravity. Okay, so this one coming down. The normal force, which is perpendicular to the surface, the force of friction, and this force X, which is the force which is causing it to slide down This could be some sort of applied force or something else, but really it's x when we turn our axis to be x like this and y. In this question, it says describe each of these blocks and describe the forces that are acting on this crate and which one gives the most acceleration. In the first example, force 1 and force 2 is greater than force 1. You can see, and they are both in the same direction. If we were doing this as a free body diagram, we could put these tip to tail like this, force 1 and force 2, and we would see that the overall net force is this. So we have a high net force in one direction, which means we have a high acceleration. In B, over here, you can see that force 1 is pulling in this direction and force 2 is pulling in this direction. Force 2 doesn't really have anything opposing it, even though we would presume that gravity might be pulling this down. But in reality, the net force, if we did the parallelogram method, the net force is in this direction. So I guess we'd be lifting the front of the box off of the ground and pulling it to the right. In this one here, force 2, the stronger force is pulling it along the ground. Force 1 could be gravity or some other force pulling it down. The overall net force in this case is in this direction, but the only one that's doing any work is force 2 because it is in the direction of the motion of the box. In the last one over here, one of these is pulling forward. We could call that the applied force, and the other one is pulling in the opposite direction, F1. So F1 could be described as perhaps the friction force. So it could be friction that's holding the box back, or it could be someone pulling in the other direction. But either way, F2 is larger than F1, which means that the net force is in this direction, although it's smaller than the original F2 because we have to subtract F1. That means that acceleration is also in this direction. So the force, the net force, is to the right, and so the acceleration of the box would be to the right. In this question, it says each arrow represents a displacement of 1 meter. So what's the total displacement in each case? Well, in case 1, the displacement is 1 meter. It's from the start to the finish, and that's the length. In question B, the distance, not displacement, is 1 meter plus 1 meter. That's 2 meters. But the displacement is from the start to the finish. It's the resultant of these two vectors. And the resultant right here has a length of the square root of 2. That's the length of an isosceles triangle, the hypotenuse on an isosceles triangle. It's also, you can get that with the Pythagorean theorem. C squared is equal to a squared plus b squared. That's 1 squared plus 1 squared is equal to 2. So c squared equals 2. So c is equal to square root of 2. In case 3, the total distance, 1, 2, 3, but what is the displacement? The displacement, again, is from the start to the finish. So it's the resultant of these. So this distance right here, since each of these is 1, then this is also 1 in this direction. In the last one, if we start at the same spot as all of the others, we've gone in a complete, well, I don't want to say circle, but we've come back to our starting point. So the displacement right there is equal to 0. These two vectors are shown right here. We can add these together in two different ways, tip to tail. So we draw one vector like this, and then we draw the other vector like this. So the resultant vector goes like this. It doesn't matter the order that we draw the vectors. I can draw the first vector like this, and then the second vector like this, and the resultant is still the exact same. We could do this with the parallelogram method if we wanted to. With the parallelogram method, they would start at the same point. One would go like this, one would go like this, and then we would draw a parallelogram out like this and out like this, and we would go from the origin to the opposing corner, and guess what? We get the same thing. So this vector, and this vector, they're all the same, like this, and like this. So either way, or any way that we draw it, we get the same resultant vector. Questions 23 and 24. Based on your answers to questions, or base your answers to these questions on the information on the diagram at right. So this is the diagram. On your on the PDF file, there was an error, and there was a little A over here. Pardon me, over here. But A should be right here. It's the position of the car. So just ignore this little A over here. If you printed the PDF and draw a new A right there, the Word document is fine, but the PDF, the A got moved somehow. In this question, the car is traveling clockwise, so it's traveling around the circle in this direction. It says draw vectors representing the tangential velocity, Vt, the centripetal force, Fc, and the centripetal acceleration, AC, of the car. Well, the velocity of the car, if we're moving around in a circle, is in this direction. So the tangential velocity is this. The centripetal force always points to the center, so this would be Fc. And since acceleration is always in the direction of the force, AC is also in the same direction. Oh, that's supposed to be an A, AC. So we have the force and the acceleration are both towards the center of the circle. So they're in the direction of C, if A is down here. And the velocity is in this direction, the tangential velocity. Notice that they are at right angles to each other. Oh, let's go back to number 24 here. I forgot that. The question says, what are the magnitudes of Fc and AC acting on the car? First, we're going to calculate AC, the centripetal acceleration. Centripetal acceleration is equal to v squared over r. So it's equal to 5 squared divided by 10. So that's equal to 25 over 10. So that's equal to 2.5. It's a point. Meters per second squared. Fc is equal to, well, force is equal to mass times acceleration. So it's equal to the mass of 60 kilograms times 2.5. That's 0.5. So it's equal to 150, and units for force are always newtons. 25. Calculate the acceleration for each graph. Well, for each graph we need to do the rise over the run, and the rise in this graph is 36 minus 12, so that's equal to 24 meters per second divided by 5 seconds. So that's just a little bit, it's a little under 5, so that's 4.8 meters per second. In this graph, the rise over the run is 45 over 5. Nope. 45 minus 15. What am I doing? 45 minus 15 over 5 seconds. So we get 30 meters per second over 5 seconds. So we end up with 6 meters per second squared. This one up here is squared too. So we're calculating acceleration. Rise over run for question C. That's 6 minus 2 meters per second over 5 seconds. So that's 4. Handwriting is bad on an iPad. 4 meters per second over 5 seconds. So that's equal to 0.8 meters per second squared. And the last one, the rise over the run, the rise is 30 minus 10 over 5 seconds. So that's equal to 20 meters per second over 5 seconds, which is equal to 4 meters per second squared. Number 26, 2 people are pushing a car with a mass of 1,950 kilograms. One person applies a force of 375 newtons. The other is 495 newtons, both in the same direction. Note that. Due to friction, the opposing force is 550 newtons. What is the net force and what is the acceleration? Now let's continue with 26. So we have 2 forces that are acting together, 495 and 375. And then we have this force right here. This one is negative. So it's operating in the opposite direction. So the net force, we can just add them up, is equal to 375 newtons plus 495 newtons minus 550 newtons. When we add all those up together, we get 320 newtons. So that's causing the car to move. And if we want to calculate the acceleration of the car, force is equal to mass times acceleration. That means that acceleration is equal to force divided by mass. So it's equal to 320 newtons. That's the net force, by the way, divided by 1,950 kilograms. And when we do 320 divided by 1950, we get 0.16, and the units are meters per second squared, if I can get that in there. All right. Number 27, the accompanying figure shows a frictionless channel in the shape of a segment of a circle. Its center here is O, and the ball rolls through the channel and exits on a frictionless tabletop at this point right here. So the ball goes around the circle and then comes out. Which path does it follow? Well, hopefully this should be obvious to everybody, but it follows a straight path, because once it leaves the channel, there's no force acting on the ball, including no friction. So the ball goes around, and when it exits the channel, it continues in a tangent to the circle, so it continues in a straight line. There's no force ever that would cause the ball to go out, and without the channel, there's no force that would make it continue in a circle. So the ball continues in a straight line in the direction of B. Number 28. A bowling ball accidentally falls out of a cargo bay of an airliner as it flies along in a horizontal direction. As seen by a person standing on the ground, viewing the plane as in the figure above, what would the path of the bowling ball most closely follow after leaving the airplane? Remember, this is kind of a perspective question. The person is on the ground, so what they're going to see is the plane moving in a straight line, and the ball will exit the plane and will continue along a parabolic path just like any projectile. So it's going to follow the direction D here. It's it's a projectile, simple projectile motion. It has an initial velocity of the plane, and it will fall based on however high the plane is. This is in contrast to a previous question that we had on another test, which was what happens when you look out the bottom of the plane. Well, if we're looking out the bottom of the plane, it appears to somebody looking out the door of the plane that the ball is falling straight down, because the plane, as the plane moves, the ball is also moving. So the ball and the plane are always directly, the plane is always directly above the ball. So it appears from the plane's perspective that the ball is always underneath it. But from the perspective of somebody on the ground, they see the ball following a parabolic path. I can't do that very well with two fingers on the screen, but hopefully you got that. Number 29. A boy applies a horizontal force of 20 newtons to a 5 kilogram box over a distance of 10 meters on a rough floor and then lifts the box to a shelf 2 meters high. What is the total amount of work done by the boy? Well, so here we have a box and a force. And the force is equal to 20 newtons, and the distance is equal to 10 meters. Well, work is equal to force times distance, which means it's equal to 20 newtons times 10 meters, which means it's equal to 200, and the units for work are joules. The next part of the question says that the box is then lifted to a shelf 2 meters high. Well, work is still force times distance, but work against gravity, the force is the force of weight, which is mg. So the force of weight is equal to mg. So the force against, or the work done against gravity, is equal to mg times the height that the ball was lifted, or the box was lifted. So it's equal to the mass of the box, which is 5 kilograms, times 10 meters per second squared, times 2 meters. And if we look at all of this, 5 times 10 times 2, we get 100 joules of work. We add those two together, and we get 300 joules. Okay? That's 200 plus 100 equals 300 joules of work done total. Now, if the box had been lifted and then carried, it's very important to understand that this work would go away, and only the lifting would exist, because when we carry something, we're not doing any work. Only when we lift. But if we push it along the floor and we actually have a force that is being applied, then we are doing work. We need work, for work to be done, we need a force applied over a distance. Two masses, 2 and 3 kilograms, are separated by a distance of 5 centimeters and exert a gravitational force F on each other. If both masses are doubled and they move so they are twice as far from each other, what is the new force? This can be treated as a ratio question. There's no need to actually calculate the exact force. We've been given all we need by being told that we have a force, and that we're doubling masses and distances. So really we can treat this as a ratio. The force is proportional to the product of the two masses, M1 and M2, over the distance between them squared. That's the inverse square law. So let's look at how we're changing these masses. We're doubling one mass, and we're also doubling the other mass, and we're dividing by the distance between them. which is also doubled, and that's squared. So 2 times 2 causes the force of gravity to go up by 4, and 2 squared causes the force of gravity to go down by 4, which means that the net force is, or the change in the force, is 1 times the original force, which means there's no change. We can do any of these the same way. If only one of the masses had been doubled, then we could include just a 1 here, and that would be 2 over 4, which would mean that the force was 1/2. Or if we had left the distance the same and yet changed the mass 2 times 2, then the gravity would be 4 times as much. But it's a ratio. Just the mass times the second mass divided by the distance between them squared. And if you enter only how much they are multiplied by the original masses and distance, then you get how much the force is multiplied from the original force.